We just introduced the idea that pH is looking at the power of hydrogen or the concentration of the protons in a solution. Water is our neutral solution, and water has a concentration of 1 times 10 to the negative 7th molarity. So that's where that 7 of pH comes from. So we're going to look at that concept a little bit more and then some calculations. So on this page, we're not going to do calculations. We're actually just going to look at the concept a bit more. But let's make sure that we can tie this pH concept to our acids and also to our bases. So in an acid solution, we're going to think about having lots of H plus ions. And then with that comes the inverse, few hydroxide ions. All right, so lots of H plus ions. Another way that I could say this is I could say I have a high concentration of H plus. And then what we're going to see when we plug that into our log equation, or actually before that, so our H plus is always going to be greater than the concentration in water. So here in water, which is neutral, H plus is always equal to 1 times 10 to the negative 7th molarity. In an acid, the concentration of my protons is going to be bigger than that, higher than that. So that means my exponents will be smaller. So it'll be -5, -4, which is more protons. Once I do the log calculations on that, I'm going to see that I end up with low pHs, and the pH I could say is going to be less than 7. How might I measure that? This is a pH probe, a digital pH probe, or we can use pH paper, or if you can see this in color in your slides online, you can use natural products like cabbage. So this is purple cabbage or red cabbage, and a lot of naturally occurring chemicals out in blueberries and cabbage and things change colors depending on what pH they're at. So these are called indicators. And so indicators are what we put into our pH paper, and if we don't want that color, then we can use a pH probe to measure pH. So we'll talk about measurements on the next page. So that's an acid, lots of H plus and low pHs. In a neutral solution, the hydronium concentration is 1 times 10 to the negative 7th. We can also say that the concentration of H plus is going to equal the concentration of our hydroxide, and we will see that we have pHs that are equal to 7. In a basic solution, we're going to have very few H plus ions. We're going to have lots of hydroxide ions, so exactly the opposite, right? We'll have relatively low H plus concentration. So in terms of numbers, we're going to see that those numbers are less than what water has. And that's going to result, when I take the log of it, in high pHs, and so pHs that are greater than 7. So those are, in words and symbols, some different ways to compare and contrast our acids and bases using pH. So you've got a couple places to practice that here at the bottom, and then we're going to move on to actually calculating some of those pHs on the next page. So looking at pH calculations, some of the calculations are easy in quadrants A and B here, and then some of them are a little bit harder, okay? Significant figures are kind of different with pHs because I've got logs. So I'm just going to tell you how it works and just follow my rule, okay? So the number of decimal places in the concentration, or sorry, not decimal places, but the number of sig figs in the concentration, so here's 2, 2, 2, 2, becomes the number of, I switched these, decimal places in the pH. So if I have 2 significant figures here, I'm going to have to the 100th place over here as my pH. All right. So remember for pH, we're looking at the hydrogen concentration, and we were looking at our exponents. So when I look at my exponent here, my exponent is 9. Change the sign on that. That means that this pH is going to be equal to 9. Because there's 2 significant figures here, I write 2 decimal places, so this would be 9.00. If you can remember back to our pH scale here, remember 7 was in the middle, and then below that, those are my acidic pHs, and above that, those are my basic pHs. So pH of 9 is going to be a basic solution. Try that again with another one. So here, look at the exponent, and the pH is going to be 3.00. That's low, so that's acidic. All right. Now, the reason I can just do these logs kind of in my head is because the coefficient here is a 1. It gets a little bit harder as you get down here to this 2.3. So now the coefficient's not 1, so I know that my pH will be somewhere around 9, but not exactly 9. All right, so down here, what I would have to do is take the pH, so I'm going to type into my calculator negative log of 2.3 times 10 to the negative 9th molarity. And when I do that, the answer that I get is going to need 2 decimal places, so that is 8.64, higher than neutral, so this is a base. If you aren't sure how to do this on your calculator, make sure that you ask for help with it, okay? So that's, if the coefficient is 1, you can just take that exponent and write your pH. If it's not, use your calculator to calculate that exact pH, but it should be close to that exponent. Over here, we can do the inverse. So if we have the pH, we can figure out the concentration. So let me show you how that works over here. If I want to solve this equation for H+, then I would say my pH equals negative log of hydronium. To get rid of the negative sign, I'm going to divide both sides by -1. So now I have negative pH equals log of H+. And then to get rid of the log, I'm going to need to raise this side 10 raised to that power. That'll cancel that out. And so over here, 10 raised to the negative pH. And so my final inverse log here is going to be 10 raised to the negative pH is equal to hydronium. So over here, what that means is if I want to know what the concentration of H+ is, it's going to be 10 raised to this power, and that's going to be 10 to the negative 5th. To show significant figures here, remember the number of decimal places is the number of the number of decimal places was the number of sig figs here, so 1.0 times 10 to the negative 5 molarity is what I'm looking at here. That is the concentration of my protons. pH of 5 is low, so this is an acid. All right, let's try that again. A little bit easier this time because we've done it once already. So pH of 12 is basic. And then I can just take that 12 and make it the exponent. So 1.0 times 10 to the negative 12th molarity of H+ is what I'm looking at there. I'll leave you some to practice. Over here, you want to be able to put this into your calculator. So the concentration of H+ is 10 raised to that negative pH. So that would be 10 raised to the negative 5.85. And when you do that, you get 1.4 times 10 to the negative 6 molarity. Let me just show you the connections here. So this pH of 5 became the negative 5 exponent. Here, if my pH is 5.85, I'm expecting to be somewhere around there for my exponent, a negative 5 or a negative 6. And notice that the coefficient of the scientific notation comes out as a non-zero, or not a 1, because it was not an exact pH. So you've got some extras to practice there. Do all those calculations, get really familiar with your calculator, and ask for help if you need it to figure out your calculator.